Thank you for the nice invitation and the nice introduction. If I'm too loud or too quiet, please let me know. Okay. So we heard already a lot about climate change and climate cooperation, and this is the topic with which I will continue in my talk. I try to continue. How does this work? Okay, so now hopefully it works. So we have been talking about climate change for a long time, more than 30 years. So the Toronto conference in 1988, that was one of the first conferences where not only climate scientists met, but also politicians. So you see how long we have been talking about this problem. And also the decision that was made at this conference was very much like the decisions that we are trying to make today. And this is the reason why I have shown this timeline not as a straight line, but more like a circle, because certain things seem to repeat themselves. So at the Toronto conference, for example, the collective goal was to reduce greenhouse gas emissions by 20%. And then some countries promised that they would do that unilaterally to reduce their emissions by 20% up to a certain year. And if you wonder whether those countries did what they promised they would do, they did not. And here's another picture, which is very much like what you have seen before. Our failure, basically, to do something about this problem. And you can see the global CO2 emissions, and you can also see when roughly the negotiations began and the effect that those negotiations had. Sometimes you can see a little drop in emissions, but this is not because of climate policy. This was more like an accident. So the last drop was, of course, because of the corona pandemic. So obviously, we were very unsuccessful. So how do we tell our students the problem of climate change and why we are failing so much? But what economists like to do, and also others, they take the very complex negotiations. This picture was taken in Copenhagen, by the way, at the climate conference in 2009, when Barack Obama was still president. So what economists do, they try to take the very complex negotiations and make it a more simple game so that they are able to understand what exactly the problem is. So one of the most simple games you can imagine, and this is what I use for my students in order to introduce the climate problem, is this one, where you have a group, and then each member in this group has two playing cards, a red card and a black card, and then every player in this group can play one of those cards. If you hand in your black card, you get 20 euros. If you hand in your red card, you get 10 euros, and everyone else in the group also gets 10 euros, and these rules apply to everyone in the group. And of course, this is the classic prison dilemma that we all know. Playing the red card supplies a public good, and the black card does not. This is free riding. So what do people do in this game? It depends. On the red side, you can see what happens in the business bachelor. On the left-hand side, this happens in my environmental econ master. So it really depends with whom you play the game, but you can also easily see what would happen if you mix these two groups. And of course, we all know that this game has been played all over the world, and cooperation is very difficult, and it's especially difficult to sustain. So this is the most simple game that we use in order to explain to our students what exactly is so difficult about this. But then the students say, but what if something truly catastrophic can happen? Would we really be so stupid to not cooperate if something very bad could happen? And sometimes it's helpful to consider other issues or other examples to approach a question like this. So we could, for example, think about this example. What would we do if an asteroid were on collision course with the Earth? This can happen with the small asteroids actually quite often, but nobody noticed. But the bigger ones, they would be noticed. This doesn't happen very often, luckily, but the possibility is not zero. It could happen. So what would we do? And this is also a question that Hollywood has asked, and it has given very different answers in these two movies. So I'm not sure if you know these two movies. The setting is pretty much identical in these two movies. Scientists find out that there's an asteroid coming to the Earth, and we have to do something about it. In the movie, on the left-hand side, Bruce Willis and a team of good-looking people, they save the world in the last minute. And the right-hand side, this movie, same setting, same asteroid, and they don't save the Earth. And what is important for my talk, and this is, I think, is also realistic, the scientists in these two movies, they can calculate exactly when the asteroid would hit the Earth. So this was important for both movies. So in the right-hand side movie, they organized a dinner for that evening to say goodbye, basically, because they knew exactly when the asteroid would hit. And in the left-hand side movie, they knew exactly when Bruce Willis has to save the Earth. So last minute. And this is very important for my talk. They knew exactly when the catastrophe would hit. So of course, these are Hollywood movies, and we cannot be exactly sure which one is more realistic. But there is an example that is close. And this is an example that actually did happen, and that was the so-called Y2K problem. So some of you may remember that was when the year changed from 1999 to 2000, and people were concerned that because of this big change in many computers and digital systems could create trouble. So you can here see on this newspapers cover, all banks will fail, food suppliers will be depleted, electricity will be cut off, the stock market will crash, vehicles using computer chips will stop dead, telephones will cease to function, domino effect will cause a worldwide depression. So this is an example that did happen, and it is similar because people knew exactly when catastrophe might hit. And again, the damage might be quite large. So was there any cooperation, or did catastrophe happen? Obviously it did not happen, and there was cooperation. So there was actually an international Y2K cooperation center that was established by the UN with World Bank funding. And also the biggest concern was that nuclear missiles could be launched by accident. And that was a very big worry. And this caused cooperation between the US and Russia, actually. So they created a center, and these people were really sitting side by side in order to make sure that this would not happen. So there was indeed a lot of cooperation. And you can also find some information for the reasons why in this case you could see a lot of cooperation. So you can find, for example, this quote: unprecedented international cooperation contribute to the successful outcome. Two attributes of the Y2K problem helped make that cooperation possible. First, Y2K threatened every nation, providing the incentive to share best practices and reduce the total cost of fixing the problem. And this is important. The unmovable deadline of January 1st gave gravity to this message. Okay, so this is what I meant before. It was exactly clear when catastrophe would happen. And this is, or this will be very important in the following, what I want to show you. So together with Scott Barrett from Columbia University, who is an environmental economist working on the climate change issue for many, many years, we thought about a very simple theory and also an experimental test to compare the cooperation level when there is something like a dangerous threshold and when we have different types of uncertainty. Okay, so in this game, we have 10 players, and this time we do not have playing cards, but poker chips. So each player has 10 black poker chips and 10 red poker chips, and every player can contribute those poker chips to the group account. And then we have the following rules for the payoff. You get 10 cents for every black chip that you keep to yourself. You keep €1 for every red chip that you keep to yourself and that you do not contribute. These two different types of chips are meant to illustrate different climate change technologies. So one is cheap. This is the black chip. You can think of windmills, conventional techniques to reduce greenhouse gas emissions. And the red chips, these are for more costly technologies. For example, this machine is something that can pull out CO2 out of the atmosphere. They exist, but they are very expensive. So this is why we have the two different chips. Then you get 5 cents for every chip that is contributed by anyone in the group. So this is the marginal benefit of reducing emissions. This is what you know from the standard linear public goods game. There is a marginal benefit from all contributions to the public good. And then we have a threshold. And the threshold in this game is 150. And if the players manage to contribute 150 chips, then that's it. There is no big loss. But if they fail to do that, then there's a collective loss of 15 for everyone. Of course, 15 is not a catastrophe, but it is a relatively large loss for people who come to the lab and expect a certain amount of money. Okay, so when we look at this game, then we can ask, what is the best for the group? So what is the social optimum? If you make the calculations, then it's easy to calculate that everyone should contribute exactly 15 chips, because then you reach the threshold and everyone gets €12.50, and that's the best the group can do. And when you then ask what is Nash equilibrium, so what is the best a single player can do? And if you do the calculations, you can think, okay, assume the others do not contribute anything. What is the best you can do? Well, then in that case, you do not contribute anything as well, because you on your own, you cannot avoid the €15 loss. But if you assume that the others are doing their fair share, the €15, then the best for you is also to contribute your fair share and to make sure that the group will reach the threshold. So in this case, we do not have a prisoner's dilemma, but we have a coordination game. But of course, this is under full information about everything. So the players know the threshold, they know the damage, and then we get this coordination game. I have shown you this game with certain parameters. If you look at the theory, you can also vary the parameter and see what happens with the game. So for example, here you see if the impact is increased, then you're more likely to get a coordination game. If you increase the threshold and the impact is relatively low, then you get a situation where the avoidance of catastrophe is not optimal. In that sense, you can say it's not really a catastrophe because the damage is very low and you have to do a lot in order to avoid it. So you rather not avoid the catastrophe. And then in the middle part, you have a prisoner's dilemma. So this is what the theory would tell us under certainty. And what we want to know then is what happens if certain things are uncertain. So Gianluca already said that there's a lot of uncertainty, and this is true. And we consider two types of uncertainty. One is threshold uncertainty, where the players do not know where exactly is the threshold. So what exactly do we have to do in order to avoid catastrophe? And the second type of uncertainty is impact uncertainty. So in that case, the players are not exactly sure what will happen if they miss the threshold. Something bad will happen, but how bad is it exactly? So there could be uncertainty also. And Gianluca already showed some examples for that. So here's another example taken from Tim Lanton and colleagues. And this is quite typical when you look in the scientific literature. They show you certain tipping events, and they give you a certain range, in this case, temperature range, and also a certain range of possible outcomes. So you do have uncertainty about the threshold, and you also have uncertainty about the impact. And this is what we wanted to see, how this affects cooperation. So when we say impact uncertainty, we say that the impact is no longer 15, but it is somewhere between 10 and 20. Okay, so the expected value doesn't change. We assume in the experiment, we assume a uniform distribution of probabilities, and we say the damage is somewhere between 10 and 20. So the expected value is the same, only that we have in one case no uncertainty, and in the other case we do have uncertainty. And if you then plug in the expected value in the game that I showed you before, nothing should change. You just take the expected value rather than the 15 that we used before, but the calculation for the players doesn't change. So from a theoretical viewpoint, this should not much affect cooperation. Of course, this is different if you change the expected value, and this has been shown by a very important paper by Manfred Milinski, where they show that if you change the expected impact, if you reduce the impact, then you reduce also cooperation. But here the focus is a bit different. It's just about the uncertainty and not about the expected value. Okay, and when we say we want to have some uncertainty about the threshold, we say that the threshold is no longer 150, but somewhere between 100 and 200. Okay, so the players in our game no longer know that 150 is enough to avoid the collective damage, but the threshold is somewhere between 100 and 200. And now the question is, what happens if we introduce that kind of uncertainty? Okay, so we do the same reasoning as before. We ask, what is the best the group can do if we now have this threshold uncertainty? And if you do the calculations, it turns out that the best the group can do is to eliminate uncertainty, so the group should contribute everything. 200, every player should contribute 20. This is the best the group can do. And then in this case, each player would get 10 euros. And now we can ask again, what happens if the players think about their own situation, not about the group, but when they want to maximize their payout given the behavior of the others. So if you assume that all the others contribute their share, so we assume everyone else contributes 20, and now I make the calculation for myself. I can either contribute 20 and then I get 10, or I can calculate what happens if I reduce my contribution to 19. What would happen then? And you can see this in this calculation here. And this is the marginal benefit that I explained before, the 5 cents for every chip that is contributed. Then this is the one chip that I decided to keep rather than to contribute to the group account. And then what happens here, and this is very important, by keeping my chip, I do not trigger catastrophe, but I increase the probability of catastrophe. But because the range now is very large, the increase in the probability is quite small. Okay, so this is this expression here. And because I only increase the probability by a tiny bit, this is actually good for my own payoff. So I get more compared to the situation where I contribute everything. So what that means is if we have threshold uncertainty, then we are back to a prisoner's dilemma. And we wanted to test this in an experiment. And this experiment was very much inspired by the literature on chemical resources. So David Budescu has done this experiment already in the 90s, I think. So that literature was really important for us. What we did, or what we tried to do, is to bring in some aspects that we thought are important for the climate problem. So we used relatively large groups, 10 players. It's not like in the other experiment that was presented before, 100 players, but 10 is relatively large. We included communication, and we included the kind of communication that you will find at the climate negotiations. So the players could make proposals for a collective target. Okay, so they could say, this is what we should do. This is my proposal. And then they could make individual pledges. So they could say, this is what I want to do. Okay, and this is what they could do in all treatments. And then we had different, we used the game that I showed you before with all the different types of uncertainty. And what was really important for us was that our participants know something about probabilities, they know something about risk. So what we did is to basically give them a lecture about probabilities, about risk, about uncertainty, to make sure that they understand everything. And we also let them practice uncertainty. So you can see this spinning wheel here. So we used this spinning wheel to let them experience and play with uncertainty. And we also used this spinning wheel to do the random draw in the experiment. So we put in a lot of effort that people really understood the uncertainty and all the implications. So I'm not saying that this is the way you should do it, but for our experiment, we really wanted to have this situation that people knew about the uncertainty, that they had a communication mechanism that is similar to the negotiations. And we thought that this is especially important because we compare a coordination game and a prisoner's dilemma. And communication, of course, can be quite helpful for coordination, but it might be much less useful in a prisoner's dilemma. So this is why we put in all these different aspects that we thought are important when you are interested in a problem like climate change. Okay, and then, as I said, we wanted to look at different types of uncertainty. So our baseline treatment is certainty. Everything is known and given to our participants. Then we included impact uncertainty. So only the impact was uncertain. Threshold uncertainty, where only the threshold was uncertain. And then finally, the combination of both, where the participants faced impact and threshold uncertainty. And otherwise, the game was exactly as I have explained it before, with the same parameters as I have shown. So what happened? So you can see here in this graph, the blue bar is the target that the participants suggested for themselves. The red bar is the pledges, and the green bar are the contributions. And you can see basically no difference between certainty and impact uncertainty. So impact uncertainty really was not very important for the cooperation level. And if anything, contributions increased. Okay, so impact uncertainty was not very influential. And this was quite different with threshold uncertainty, where people made a quite ambitious target. The pledges were already lower than the targets, and then the contributions were much lower than the pledges. So, of course, the behavior was different from the theoretical predictions, but you could see a big difference, nevertheless, between impact uncertainty and threshold uncertainty. And the difference becomes even clearer if you do not look at contributions, but if you look at how often the damage occurred. And this is shown in this figure here. So this is the probability that the collective damage occurred. And with certainty and impact uncertainty, the damage was avoided very, very often. And this was quite different with threshold uncertainty. And we use this game also for some other settings. So for example, if you have not only one threshold, but a couple of smaller thresholds, things get only worse. This is what the theory would predict, but this is also what we find in experiments. Also, when you change from risk to ambiguity, so when people do not even know the probabilities anymore, things become even more difficult. So all this is quite frustrating and sad. And when I read the interview with Ivo de Boer, he used to be a UNFCCC executive secretary, and he gave an interview. And then in this interview, they asked him, would you call it insanity to know catastrophe is coming and do nothing about it? And he said, no, I don't think it's insanity. I think it's reality. So when I read this interview, it reminded me very much of our experiments. But of course, I do not want to end with this very pessimistic outlook, but I do want to talk a bit more about the Paris Agreement. So the interview was before the Paris Agreement. So now, of course, we are faced with the question, does Paris make a difference? And Gianluca already said that Paris is making a difference, but the question is it enough? Can we be optimistic about the future because we have the Paris Agreement? I have here another statement from Christiana Figueres. She also used, at the time when the Paris Agreement was negotiated, she was the UNFCCC executive secretary, and she was very optimistic after Paris. So she said right after the conference, to have Paris is a huge flame of hope. But of course, you can also find other opinions about the Paris Agreement. For example, James Hansen, he's a climate scientist at Columbia University. He basically said that Paris is just cheap talk and nothing else. So opinions are quite different. How optimistic we can be. So how is Paris different to the other outcomes of the climate negotiation? And I think this quote here shows one of the differences that Paris tries to make. That was published in the New York Times right after the Paris conference. Here's another way to think about it. You are given a school assignment, but there won't be any punishment if you don't turn it in. However, you are required to attend an assembly with your peers and to show them your homework. The hope is that the student leaders, the largest economies, will create a dynamic of international pressure. Okay, so one important aspect of the Paris Agreement is to create a naming and shaming system where the different actors in the negotiations will start pointing fingers at each other, and that this can create a pressure to make sure that everyone is increasing the ambition and the efforts. So we know from many experiments that shaming and pointing fingers can have a very dramatic effect on individuals' behaviors. So there are many, many experiments that, for example, showed if people are observed, they behave much more pro-social than when they're not observed. But the thing is that when we talk about climate, decisions are made by governments or by delegation teams, by groups. And can we have the same optimistic expectation about naming and shaming when it comes to groups? And this is what we tested in an experiment. So in this experiment, we used a very standard public goods game. And in one version, we had individual players that could contribute to the public good. And in the other version, we had teams that contributed to the public good. And in order to induce a kind of naming and shaming mechanism, after each round, we showed the contributions together with pictures of the different contributors. And we played this game over 10 rounds, quite standard. And in this treatment, only one person would be shown with the contribution. And in this other treatment, the whole team would be shown that has chosen a certain contribution. And what we wanted to show is, or to see, if naming and shaming works the same for groups as it works for individuals. And here's the result. So the blue bar and the red bar, this is for the individuals. And you can see that the contributions are more than doubled for the individuals. And this is what we knew before from other studies. So naming and shaming was very effective for individuals. And then green and yellow, these are the contributions for the teams. And you can see that the increase is much smaller. Of course, the overall level is higher, so groups cooperate better than individuals. So you can say, well, this is a kind of ceiling effect. There was a lower need for naming and shaming. But if you look at the contributions over time on the right-hand side, you can see that this is only true for the first half of the game. So in the second half of the game, the teams also have difficulties to cooperate. And then the pictures could have made a difference, but they didn't. And we also looked deeper into the data to compare, especially the people who are very prone to feelings of shame. And we could see that these individuals are very sensitive to pictures when they play alone, but they are not sensitive to the pictures when they are in a team. So being in a team protects you from feelings of shame, and this clearly limits the potential of naming and shaming. Okay, so of course, these are experiments with students, and they have all the problems that we always have with student experiments. So what I want to show you at the end is some results from a survey with climate experts. So this is joint work with Marcel Umkowski. He's a PhD student in Kassel, and David Victor. David Victor is a political scientist in San Diego, and he has always been interested in the climate negotiations. And so we have invited to this survey people who go to the climate negotiations, so who are part of delegation teams, and also people who work for the IPCC. So we have both negotiators and scientists. And we have a bit more than 800 individuals. For those of you who are doing surveys, this might look like a really small number, but these people are really difficult to get. So actually, I think this is the largest sample I've been aware of with this kind of people. So we tried our best to get as many as possible. And also the distribution around the world was not even, but we did our best to really get people from all over the world. And we asked them many different questions, and I show you only 7 to give you a flavor. And I hopefully have chosen the most important questions to show you. So here this question is about the long run perspective. How optimistic can we be in the long run? So in particular, we ask, how confident are you that by 2050, countries overall will be able to replace fossil fuels to a large extent by alternative energy sources? So on the left-hand side, we ask about countries overall. Okay, so will the world as a whole manage to replace fossil fuels? And on the right-hand side, same question, but only about the home country. Okay, so for each negotiator and for each scientist, we said, okay, now think about your home country. Do you think your home country will be able to do that? And in this figure, of course, you can cluster people in different categories. In this figure, they are clustered by the degree of democracy. So we have used the Freedom House Index that assigns countries either into free, partially free, or not free. And you can see overall, there's not much of a difference, and they are not super confident, unfortunately, that this is possible. On the right-hand side, you can see that at least the negotiators and the scientists from the democratic countries, they are a bit more optimistic that their home country will be able to do that. And the next slide provides some insights why there could be these differences between the different types of countries. So here we ask, what do you think is the most important motivation for the fulfillment of your home country's NDC? So this is the national determined contribution. So this is basically the promise that a country has made. And we have asked, what is the motivation to fulfill the promise for your home country? And again, we clustered the responses according to the degree of democracy. And when we start on the right-hand side, okay, so these are all the respondents from the democratic countries. And you can see what is important for them: to mitigate global climate change, pressure from civil society, economic growth, and improve national reputation. So these were the important factors for them. And you can see also that this is quite different for the other types of countries. Some, of course, is quite plausible. Civil pressure is much lower. Also, our national reputation is much lower. Economic growth is by far the most important motivation, more important than to mitigate global climate change. Okay, so it is always hard to find something optimistic to say about climate change. But I think if I have to pick something that could be optimistic, it is the pressure from civil society for the democratic countries. I think this is also related to what Gianluca said. It can have an effect, so this is important. And I think it is evidence in this survey that it can make a difference. And then for the other countries, I think the truth is we have to pay them in order that they are prepared to do something. I think that's a very clear message from this research, but also from many others, that if we want them to do something, we basically have to pay them. Another issue, and this is almost the last thing that I have to say, is there is this idea, and I think I saw a slide about Nordhaus club idea. So this is discussed a lot, especially among environmental economists. So could we form a club, like a coalition of the willing, and then use trade measures to convince the others to join the club? So this idea has been around for a while. And this is also something that we ask the climate experts, what they think. Is this legitimate? Is this useful? Is this risky? And you can see that there are quite different opinions. So this time we have grouped the answers according to OECD Europe, the rest of OECD, and North America, and then the others. You can see it below the figures. And what is quite remarkable, I think, is this one. So Europe is really exceptional when it comes to the perceived riskiness of linking these two issues. And Europe is also the only region that is trying to do it. So apparently there is a big gap between regions and how they perceive this possibility. So I think this is all I have to say. A quick summary, what I tried to show you. So the existence of a dangerous threshold can definitely help cooperation, but if there's a lot of uncertainty about what exactly we need to do, then cooperation is not guaranteed. And Paris makes a difference for sure, but it may not be enough. So I think more pressure, more measures like linkage, trade, and climate policy are needed. And only the prospect that something bad could happen, I think, will not be enough. Thank you.